What's up, mathematicians? Welcome back to our lesson on proportionality and similar triangles. In the last video, I introduced the idea of proportionality, using it to solve a couple problems, including finding the height of a tree. In this video, I want to take a closer look at similar triangles. So that is the focus of our video, this one right here. So similar triangles. And before we get started on the calculations of similar triangles, some example problems, that sort of thing, I'd like to give you a definition for what similar triangles are. So let's get that up here. You may want to write this down in your notes if you're taking notes. So this is my definition. You might see other definitions elsewhere, but at least at this point, our working definition of similar triangles will be this. Two triangles are similar if all their corresponding angles are equal and all their corresponding sides are proportional. Okay, now you might look at this definition and think, there's a lot in that definition. You know, can we just accept all those things? Is there maybe a theorem somewhere in this definition? Maybe there is, and we will investigate that more in a future unit. But for now, we're going to stick with this as our definition of similar triangles. If two triangles are similar, then all the angles are equal, and all the corresponding angles are equal, and all the corresponding sides are proportional. Okay, so now let's dig a little bit deeper into that definition, what it means, by looking at a couple triangles. So you see here on my paper, I have two triangles drawn. A smaller triangle, ABC, and a larger triangle, DEF. Now, these two triangles are similar. And in order for them to be similar, we know two things, right? We know, number one, that all the angles are going to be equal. So actually, let's write out the similarity statement first. So we're saying that triangle ABC is similar to triangle DEF. So this little line here indicates similarity. So it follows, if these two triangles are similar, that angle A must be equal to angle D. Those are corresponding angles. Angle B must be equal to angle E, again being corresponding angles. And finally, angle C must equal angle F. Okay, so that's the first part of the definition, right? That all the corresponding angles are equal. What about the second part? Well, the second part says all the corresponding sides are proportional. So in order to sort of notate the sides, the typical, the sort of standard way, convention in geometry is if you have angle B here, you go to the side opposite that angle and you use a lowercase b, so a lowercase letter, opposite the angle. So this is angle A, and so we're going to call this side A. This is angle C, we're going to call that side C. We'll do the same thing here. We'll put D, E, and F. So now that I've signified what these sides are, let's go ahead and write out our proportionality statement. So we know that corresponding sides are proportional. So that means A is proportional to D. So the ratio of A to D is equal to the ratio of B to E. So we'll say B over E, which is also equal to the ratio of F to C. I'll put here F over C. So this is our proportionality. This is saying our angles are equal. This is saying that the sides are proportional. Now, sometimes when you're doing problems with similar triangles, you might use a different ratio. For example, you might say that A to C is equal to D to F. That might seem like a different proportion, but it turns out that maybe I'll just write that statement right here. I'll do it in a different color. So I could say that A over C, this over this, is equal to D over F. So I can say A over D is equal to C over F, or I can say A over C is equal to D over F. Now these two might seem different, but it turns out that given this one, it's pretty easy to derive or prove this one. I'm not going to do it, but I encourage you to try that derivation yourself. It's not too difficult, just involves a little bit of algebra. But now we're going to move on to some example problems. Okay, here is example problem number 1. We see two triangles right here, and as indicated, these corresponding angles are equal. So these two angles are equal, these two angles are equal, and those two angles are equal. So since the angles in this triangle are equal to the corresponding angles in this triangle, these two triangles are similar. And now we can see these distances specified. So we're going to say that's 10, this is 12, this is 24, and then this length here is x. This is the thing that we want to find out. So we'll just set up our proportionality equation. So we can say, all right, the length 10, this is proportional to corresponding side, so 24. And this is equal to this length 12 over the corresponding side, which will be x, the unknown. And we cross multiply this, so 10 times x is 10x, and 12 times 24 is 288. Okay, so in order to solve for x, I just need to divide both sides by 10. These cross out, and I get that x is equal to 28.8. So that's the answer. So not too bad, right? Now, if you recall, I mentioned up here that you could set the proportionality up differently. I'll write it. I'm not going to go through the process of solving it, but I would encourage you to do that and see that you will get the same answer. So to set it up the other way would involve writing it, let's see, I'll write it here. So I could say, set it up as 10 over 12, this over this, is equal to 24 over x. So this over this is equal to this over this. Go ahead and try to solve that, and just to verify that you do indeed end up with the same answer. Okay, now let's move on to example number 2. In this example, we see that one triangle is embedded inside a larger triangle. And we can see, because of this situation, that this angle up here is shared by both triangles. So clearly it's the same in both triangles. We're also going to go ahead and say that this angle is equal to this angle, and that angle is equal to that angle. So because the three angles in the smaller triangle are equal to the three angles in the larger triangle, these two triangles are once again similar. Now we're going to try and solve for x right here. Now keep in mind that x is the length of this smaller segment, not the length of the whole line. So we're going to need to keep that in mind as we set up and solve this problem. So let's set up the ratio of these sides first, right? So we have 8 to 14. So I'll write that. So 8 over 14. And now we'll do the other length. So this is length 12 in the smaller triangle, right? 8 is in the smaller triangle and 12 is in the smaller triangle. Now we need this length, this corresponding length in the larger triangle. This whole length is not x. X is only this much. This whole length is the combination of 12 and x together. So it's actually 12 plus x. So this is the proportion that we need to solve. So we can once again cross multiply. We have 8 times 12 plus x. So 8 times 12 plus x is equal to 14 times 12. Well, let's see. 12 times 12 is 144, plus 12 is 156, plus 12 is 168. So 14 times 12 is 168. Now I'll go ahead and distribute this 8. And I get 8 times 12 is 96. And 8 times x is, of course, 8x. And this expression is equal to 168. Okay, now I can subtract 96 from both sides. These cross out. Now, 168 minus 96 is pretty close to 168 minus 100, which would be 68. But 4 less than that, which means that the answer is going to be 4 more than 68, so 72. And then we have 8x on the other side. Dividing both sides by 8 gives us the result that x is equal to 9. So there, oops, sorry about that. X is equal to 9. So this quantity, or this length right here, is 9 units long. If you want to know the whole length, well, you can just do 12 plus 9, and you can see this whole length here must be equal to 21. Okay, let's move on to the last example for the video. Okay, so here's our last example on similar triangles for this video at least. And in this particular problem, you can see we have two triangles. There's a perpendicular here, and so both of these angles are right angles. These two angles are equal, and these two angles are equal, which means these two triangles are similar because the 3 corresponding angles in the small one are equal to the 3 corresponding angles in the larger one. Another thing to keep in mind here is that, this length is 6, this length is 8. Those are the segments, and we're actually trying to find this whole length over here, even though we're given this base and this base as expressions in the variable x. So it's going to be a little bit more algebraic work to solve this one. But as I think you'll see, it's still not too bad. First thing we need to do, we need to set up our proportionality equation. So let's see here. We have, let's start with a small triangle, and we'll go ahead and say that this length 8, so 8 over this base, I'll do the ratio this way, this base, which is 2x minus 2, is equal to, now let's go to the larger triangle. So this whole length is equal to 6 plus 8. So that's going to be 14. And this whole length right here, the base, is 3x. Now what we can do is cross multiply, as we've done in the past. So we have 8 times 3x. So let's see, 8 times 3x is 24x. And this is 14. I'll just write this way. So 14 times 2x minus 2. So I'll need to distribute this 14. And I get 24x is equal to 28x minus 28. Doing problems like these, sometimes you realize why it is that it's important to get some basic algebra skills under your belt before taking a geometry course, which often will include this type of problem. So hopefully we're able to move through these algebra steps pretty smoothly by this point. Now we need to get x by itself, and so we're going to subtract 28x from both sides. These will cancel out. I'm going to get negative 4x is equal to, well, I'll just bring down this negative 28. And now I'll divide both sides by negative 4 to get the value of x. And negative 28 divided by negative 4, well, a negative divided by a negative is a positive, and so this is going to be positive 7. Okay, so the value of x in this diagram is 7. However, what I asked you for is not the value of x, but this total length right here. So now what we need to do is we need to plug 7 into both of these expressions. So we have 2 times 7 minus 2. Well, that's going to be 14 minus 2, which is equal to 12. So this length here, I'll just write it in there, is going to be length 12. Now this one right here, let's see, 3, plug 7 in for x, and I'm going to get 21. And so the length of this base of the larger triangle is 21. Now to get the full length, I just add these two together. And 12 plus 21 is equal to 33. So right there is our final answer. So the length of this unknown side, the total of these two bases together, is 33. Okay, so hopefully going through those examples has helped you see how we can apply this concept of similar triangles to some more abstract proportionality problems. Of course, I do think it's important to always keep in mind that this stuff can be applied to the real world as well, which is why in the last video I showed you the example with the tree and the example with a map even as well. So you can see that proportionality does apply to the real world. There are many other situations in which it does. We're going to be using proportionality a lot in the rest of the unit. We're going to move towards trigonometry, and trigonometry is really all about proportions. So that's another reason why it's important to talk about it now. So I hope this was helpful, and thank you again for watching. We'll see you in the next video. Bye-bye.